In lecture 1a, we mentioned about Lorentz force in our effort to define magnetic induction vector B. In this lecture, we will discuss some application of Lorentz force, namely charged particle in a magnetic field, and we will do some problems, theory, and continue our discussion in part 2. Now, Lorentz force on a particle having charge q and moving with velocity vector v in a region where there is a magnetic induction vector b is given by this expression. So this force is felt by q as it enters a magnetic field. If a force acts on it, that is on the particle, there will be an effect of the force. Now in this lecture, we will study what the effect is. It is clear that the particle will manifest the effect on it through a change of its course or change of its path. So ultimately, the problem reduces to determination of particle trajectory. As we know the structure of Lorentz force, let us start by solving a few problems and then come to the evaluation of the nature of trajectory of the charged particle in a magnetic field. So this is the first problem that we take up. We have to find the work done as well as the power delivered by Lorentz force on a particle. The particle is of charge q and it is moving with velocity vector v in a magnetic induction B. Now this is the Lorentz force. The definition of work done by a force vector F upon a particle in moving it a distance by an amount vector dr is given by this expression, and the total work is obtained by an integration. Now dr can be written as dr dt into dt, and dr dt is v, so that we end up with f dot v. Now here F is the Lorentz force, so we can put it here, and therefore the integrand is a vector triple product which involves vector v twice, and therefore this is 0. The calculations can be done, and you did it in mathematical physics class. So work done turns out to be 0. Now here one thing should be very clear. Here work is 0 does not imply that energy is 0, because every body has some energy. What we mean here by mentioning that work is 0 is that it does not have to spend any energy to do any work. That is, there is no change in its energy, and hence there is no work done. So we conclude that magnetic Lorentz force does not do any work on particle. A very important conclusion. Now what about power? Rate of doing work is called power, and the expression of power is F dot V, as you know it from mechanics class, and F is the Lorentz force, so we can put it here, and again a vector triple product involving velocity twice comes in, and therefore power is 0. Let us note that power is 0 and power is dw dt, rate of doing work, so rate of doing work is 0. Again, if we spend energy, we are doing work, and the rate of expenditure of energy is equal to rate of doing work. So rate of doing work is equal to rate of expenditure of energy. Since this is 0, this will also be 0. Here K is kinetic energy, the expression of which is half mv square. So d dt of half mv square is 0, which means therefore that the kinetic energy half mv square is constant, and this means v is constant, that is velocity magnitude is constant. The particle entered into the B region with velocity vector v, and vector v has two parts, its magnitude, its direction. Now what turns out to be is that velocity magnitude is constant, the direction may change. So we can ask, what is the effect of Lorentz force? It does no work on the particle. The velocity of the particle is fixed, the kinetic energy is fixed and the Lorentz force bends or deflects the particle. The particle, so to say, curls up as evident from a change in direction of its velocity. So the next problem that we address is, does magnetic induction vector B always bend a charged particle? So this is the Lorentz force, this is V, this is B. The included angle is theta. And if we write down the cross product, we have this thing. Now two cases can be thought of. One is theta equal to 0, for which sin theta is 0. Another is theta equal to pi, for which again sin theta is 0. Now if sin theta is 0, then this means that force is 0 in both the cases. Now theta equal to 0 means V is parallel to B, and theta is pi means that V is anti-parallel to B, or V is parallel to minus B. So in both cases force is 0. Now since force is 0, it follows from Newton's first law of motion that the particle will continue to remain in its state in which it was, and therefore the trajectory will be a straight line in this case. So does B always bend a charged particle? If the charged particle is parallel or anti-parallel to the magnetic induction, then it will experience no force and there is no question of it being curled up or bent or deflected. It will move on straight. We next discuss another problem. What is the magnetic force on a charged particle which is at rest? So if we write down the Lorentz force and put V equal to 0 because the particle is at rest, then we end up with a 0. So only moving charge experiences a Lorentz force. A charge at rest will not experience a Lorentz force. And this is ensured by presence of V in the Lorentz force relation. The next problem is, a charged particle is projected in a magnetic field with certain velocity, and that velocity is parallel to the field. What will be its trajectory? And the options are circular, helical, does not care, and continues to move unchanged along a straight line, or it comes to rest on entry to the field. Now this is the Lorentz force. V parallel to B means force is 0. So as per Newton's first law of motion, it continues to move unaffected. So the answer is C. So C is the answer, it doesn't care. Let us now make a brief discussion on when Lorentz force is 0. So this is the Lorentz force and this is the explicit expression of it. And force is 0 if Q is 0, that is if particle is neutral, it experiences no Lorentz force and it will move along a straight line. If velocity is 0, then Lorentz force is 0. So velocity is 0 means particle is at rest, so it will continue to remain at rest because force is 0. Next is if B equal to 0, that is if there is no field, then there is no force experienced by the particle and it will move in a straight line. If, as discussed earlier, if theta is 0 or pi, that is if velocity is parallel or anti-parallel to B, then also the particle will not experience any force, and as per Newton's first law of motion, will continue to move in a straight line. So these are the situations where particle experiences no Lorentz force. The next problem, this is a region where there is a magnetic induction and this B points into the paper, so it points down into the paper. An electron enters into it, so we use the initial velocity, this is x, this is y, and certain options are given. We have to choose among these the correct option. Here v is the speed at a later time. Now, as discussed previously, that when a charged particle enters into a magnetic field, it experiences a Lorentz force, and that Lorentz force bends it in general but does not affect its velocity, and therefore the velocity will remain fixed. So if the initial velocity magnitude is u, so will be the velocity at any later time. So velocity magnitude won't change. So these two options are ruled out and we have these two options, v unchanged. Now we have to decide in which direction the particle will move. So the particle enters into the region in this direction, so it is along x, and B is into the paper, so it is down, and therefore Q into V cross B gives rise to a Lorentz force which is in this direction if the particle is positively charged. But since the particle is negatively charged, it will not be along y, but it will be along negative of y. So we come to the answer that this is the correct choice of force. So y should be negative, and therefore out of these two options, B will be the correct one. So the answer is B. Let us consider another problem. In this problem, this is the velocity, this is the magnetic induction, and this is the angle theta. Now in this problem, the angle theta varies, and there are so many options given, and we have to find for which angle the response of the particle, the charged particle, will be maximum. This is Lorenz force, and we write it explicitly. Now this Lorenz force has two parts. One is QVB, which for this problem is same. So everything is decided by sine of theta. So there are 5 cases, and we have put the values of theta here. Theta equal to 0, 45, 90, 135 and 180, and on evaluation we find that sine 90 is 1, and that is the maximum. Obviously sine 90 being maximum, the force corresponding to it will be maximum, and therefore the response will be maximum. So the answer is therefore C. Having discussed few problems, we have learnt quite a few things, and they are as follows. When a charged particle enters a magnetic field, it experiences a Lorentz force that deflects or bends it or curls it and prevents it from following a straight line. Of course, its velocity should not be parallel or antiparallel to the magnetic induction. The second thing that we learnt is that the particle responds to Lorentz force such that its velocity does not change, but direction of velocity changes. Let us now go straight into theory. We consider a special case where a charged particle is projected at an angle 90 degrees with magnetic induction. We consider non-relativistic motion, that is low speed case. Magnetic induction B is constant, and it is along z hat, which we take to be pointing into the paper. M mass of the particle, Q is the charge of the particle. Now we have to study this diagram carefully and understand the trajectory before going into any meaningful mathematical analysis. The cross marks indicate the direction of B, which points downwards into the paper, and this is the direction of velocity. So the charge Q enters normally into the magnetic field, and P1 is the point of entry. Now what happens at P1? This is the magnetic induction that points downwards. This is the velocity of the particle. At P1, particle experiences a force Q into V cross B, and V cross B means this force. So it experiences a force in this direction. We can verify it from a right hand rule relation. Since this is V and this is B, so V cross B means the force is along this direction. So obviously the force at P1 experienced by the particle will be P1O. So the particle cannot move straight, but it bends. Suppose it bends and comes to the point P2. What happens at P2? This is the magnetic induction acting downwards at P2, and this is the velocity of the particle trying to move off the tangent, and then this will be the force Q into V cross B. So this will be the force acting on the particle, which is again along P2O. In other words, this is the velocity of the particle, it trying to follow a tangent at P2, but it feels a magnetic induction downward, which means the force, Lorentz force that acts on it is along this direction, which is therefore P2O. And therefore it cannot go straight off the tangent, but it bends again. And suppose it comes to P3, and what happens here is that it tries to move off the tangent. So a Lorentz force acts on it, which is along P3O. And therefore it cannot go straight, but it bends again, bends further, and comes to P4. The same thing happens at P4 again, and therefore the particle is attracted by a force along P4O, and similarly at P5, where it experiences a force along P5O. Now P1 is the entry point, and the particle tried to move straight, but the magnetic field B curls it, and therefore it doesn't follow a straight path, but it curves or bends and moves along a circular track. So this is the trajectory of the particle. The description that I tried to give to make you convinced that the charge follows a circular track P1, P2, P3, P4, P5 from entry point P1 to the exit point P5 is given here. Why is the track circular? This is easy to understand, though we will prove it in a rigorous manner. The forces, the F's, are due to cross product of V and B, and so are perpendicular to the velocity V, which is along the tangent. So F is perpendicular to V, so V is along the tangent, and therefore F is along the radius. So forces are directed along the radius, and two such F's will intersect at some point, and that will determine the center of curvature of the track. So Q traces a circular track in the XY plane. Now why the XY plane? This is because the Lorentz forces F's are all perpendicular to B. We can take B along, say, Z axis, and so the F's will lie in the XY plane. So the bending of the particle occurs in the XY plane. A particle will move in a circle under the influence of a center seeking force that we call centripetal force. The magnetic Lorentz force curls or bends the charged particle Q, and thus provides the necessary centripetal force. So we can equate the centripetal force with the Lorentz force as shown here, and this gives us mv equal to q rho b, which is a very important relation. And from here we have v equal to qb by m into rho. Now this factor qb by m represents a frequency as evident from this dimensional calculation. It has a dimension of 1 by time, or 1 by second is its unit. We call it omega. This is the frequency with which Q circulates in the circular track. It might be a half circle or a full circle or a quarter of a circle, but at least it is a part of a circle. This frequency omega is called cyclotron frequency or gyrofrequency. It is the frequency with which charged particles move in circular tracks in a particle accelerator called cyclotron. We shall discuss cyclotron in a separate lecture. The time period is given by this expression, and the linear frequency is here. A very important point is that these frequencies omega nu and the time period depends upon the charge, the mass, so it depends upon the charge to mass ratio, and it depends upon the magnetic induction. It does not depend upon the velocity of injection v. The radius of the circular track is denoted by rho and is given by v upon omega. If we put the value of omega, that is qb by m, we end up with rho equal to mv by qb. Now mv is momentum denoted by p, so rho is p by qb, a very important expression. And the kinetic energy denoted by k is p square by twice m. Using this, we end up with this relation between radius of curvature and the kinetic energy of the charged particle. The beauty of this problem is that through reasoning and using superficial or cosmetic arguments, we have arrived at the answers to most of our queries regarding nature of trajectory, frequency, time period, radius of the circular track traced. We also have to discuss another very important aspect, namely the nature of traverse of the circle, whether clockwise or anti-clockwise, or whether the circle is left-handed or right-handed. This also can be done immediately without going into rigorous calculation. Let us refer to this figure. This is the magnetic induction which points downward, and consider a positively charged particle entering into this region perpendicular to B. So here it comes and it is influenced by this magnetic induction pointing downwards due to this Lorenz force which bends it in this direction. So the positively charged particle will enter and it will just bend in this direction. So this is the track of the positively charged particle due to this Lorentz force, and obviously the track of the negatively charged particle will be in the opposite direction. So this is the track of the negatively charged particle. Now clear that this is anti-clockwise motion, but this is clockwise motion. Again, if our thumb points along B and you curl your fingers, then this is the trajectory, this is the track which we obtain for the negatively charged particle. So negatively charged particle traces a right-handed circle, but the positively charged particle traces a left-handed circle. What if B points upwards? In this diagram, B points upwards towards the reader. Consider the motion of a positively charged particle in this region. So here it comes and it finds B in this direction and it experiences a Lorentz force in this direction. So it will bend along this curve, and therefore this is the track of a positively charged particle. The opposite happens to a negatively charged particle, so the track will be of this type. Clearly, now the positively charged particle has a clockwise motion while negatively charged particle has anti-clockwise motion. And regarding the handedness, if the thumb is along B, then now we find that the negatively charged particle executes a right-handed circle while a left-handed circle will be executed by the positively charged particle. We can compare the two diagrams if we keep them side by side. Let us introduce now a bit of rigor into our discussion of charged particle moving in a magnetic field. Let us state why. We do not yet know the equation of motion, the equation of trajectory followed by the charged particle in the magnetic field, the coordinates of the center of circular trajectory, the time spent in a magnetic field, velocity at any point in the trajectory, and there are a host of endless questions. And for any problem, one should do a systematic and rigorous derivations and then discuss things. So let us write down the equation of motion, and here it is. We have to take help of two famous equations. One is Newton's second law of motion and the other one is Lorentz Force law, and combined we end up with this equation and then expand V in Cartesian coordinates and write the cross product in terms of a determinant, and here Vz is 0 because V is perpendicular to B as stated earlier. Equating the components of x cap, we get the x equation, and equating the y cap components, we end up with the y equation. Now these equations involve an omega, and this omega is qb by m, and we showed that it has dimension of frequency. Since we are sure from our previous analysis that the charged particle traces a circle, let us assume trial solution involving cosine and sine as this one. Here omega 0 is the frequency of rotation, c and d are constants, this is the phase part, and phi is the epoch representing the phase at t equal to 0. Now we can put this trial solution in the x equation and y equation, and then what we get is d equal to plus minus c. So this is how the constants are related. We thus have two choices or options. One is d equal to c and the other is d equal to minus c. Again, the particle entering into the magnetic field can be negatively charged or can be positively charged. We thus have to write correspondences. For a negatively charged particle, that is for q equal to minus mod e, let us choose d equal to c, and this leads to omega 0 equal to mod e eb by m. For positively charged particle, let us choose d equal to minus c, and this leads to omega 0 equal to mod e b by m, which is equal to omega as we got previously. So we get the same omega 0 for the two cases, and also this omega 0 is equal to omega. So we have determined the frequency of rotation, which is omega 0, which we will now call omega, and is equal to mod e b by m, and it is called the cyclotron frequency. Now what if we made the other choice? That is, what if we took d equal to minus c for negatively charged particle and d equal to c for positively charged particle? Simple calculation shows that will lead us to a negative frequency, which is absurd, and therefore this choice is not correct. The earlier choice which we made was correct. We note that whatever be the charge of the particle, the angular frequency of rotation of the charged particle in a magnetic field is given by this expression, which is charge into field by mass. Let us make a gist of what we did, and here it is. For negative charge, that is for q equal to minus mod e, d equal to c, and so we have this thing. And for positive charge, that is for q equal to mod e, d equal to minus c is the appropriate choice, for which we have this equation. Now we are in a position to calculate v, which is under root vx square plus vy square, and it gives c, since sine square plus cos square is unity. So we get the value of velocity to be constant, that is velocity magnitude is conserved, same at t equal to 0 as well as at any future t. But Vx and Vy are functions of time due to the presence of cos and sine. Also clear that kinetic energy, which is half mv square, is conserved. And this we showed in the first problem we did, and it follows from the fact that Lorenz force does not do any work on the particle. Also evident that momentum p which is mv, is conserved. Now, having obtained the velocity components, we now proceed to find the trajectory of the particle, which we suspected to be circular. Equation of trajectory means we have to obtain equations relating x and t, y and t, and then we have to eliminate time and therefore connect x and y, and finally we will plot the trajectory in the xy plane. Now let us evaluate x and y in our effort to obtain the locus or trajectory of the charged particle in a magnetic field. For negative charged particle, this is Vx, and for positive charged particle, this is Vx, and we see that they are same. Now Vx is dx dt, so integration leads to this equation, which involves a constant of integration alpha. At t equal to 0, if x is x of 0, then substitution gives us the value of alpha. So this is the x equation in terms of time t. Here the value of rho is v by omega. Now the y equation. Now these are the y equations. They are different for the two charges. Now putting dy dt for Vy and integrating, we end up with these equations involving the constant of integration beta minus and beta plus for the two charges respectively. Now at t equal to 0, putting y equal to y of 0 and using rho equal to v by omega, what we get is the values of beta minus and beta plus, and since these are determined, we end up with the y equation for the two charges in terms of time t. We now eliminate t from the x equation and the y equations by squaring them and adding. Now since sine square plus cos square is unity, we have these equations which represent trajectory of the charged particle in the magnetic field, and these equations represent circles. So we conclude that the motion is in xy plane since only x and y are involved, and secondly it is circular as evident from the structure of these equations. For negatively charged particle, these are the coordinates of the center, and for positively charged particle, these are the coordinates of the center of the circle, and the radius is rho, and this rho can be connected to momentum and kinetic energy through this equation. Now the plot. 0 0 represent origin, and the centers are here. Alpha beta minus is the center of the trajectory, followed by the negatively charged particle. Alpha beta plus is the center of the trajectory, followed by the positively charged particle in the magnetic field. Now this is alpha, and this one is beta minus, this one is beta plus. Let us now find the sense of traverse of charged particle, both positive and negative, along the circular track. We have collected the equations connecting x and t and y and t. Now we have to check the location of the particle at two instants, say at that value of t for which omega t plus phi is 0 and pi by 2. Now at omega t plus phi equal to 0, we have sine of omega t plus phi equal to sine of 0, and therefore x is alpha, and x is alpha here. At omega t plus phi is 0, cos omega t plus phi is cos of 0, which is 1, and therefore we have y equal to beta minus plus rho here and y equal to beta plus rho here. Again, at omega t plus phi equal to pi by 2, we have sine omega t plus phi sine pi by 2, which is 1, and so we have x equal to alpha plus rho here and x equal to alpha plus rho here. And at omega t plus phi pi by 2, we have cos omega t plus phi as cos pi by 2, which is 0, and therefore y equal to beta minus here and y equal to beta plus here. Now let us come to the plot. The origin is here, and this is x-axis and this is y-axis, and so x to y gives us z, which points vertically down, and we take the magnetic induction downwards. Center is at m minus for negative charge and m plus for positive charge, and the coordinates are, this is alpha and this is beta minus. Here this is alpha and this is beta minus. Now let us identify one position of the particle, say P1. Now for negative charge, the coordinates are x equal to alpha, so we are here, and y equal to beta minus minus rho. Now this is beta minus rho means we are here, so this is the location of the negative charge at omega t plus phi equal to 0. And similarly, in this case x equal to alpha means we are here, and y equal to beta plus rho, this is beta plus rho means we are here. So this is P1, which is the location of the positive charge at omega t plus phi equal to 0. Now at omega t plus phi equal to pi by 2, the coordinates change and x becomes alpha plus rho, which means the particle is here, x coordinate, and y coordinate becomes beta minus, so beta minus means the particle is here, and therefore this is the location of the particle at omega t plus phi equal to pi by 2. For the positive charge, the location x coordinate is alpha plus rho, so it is here, and y is beta plus, so it goes up and beta plus is here. So P2 is the location of the charge at omega t plus phi equal to pi by 2. So we have located the position of the particle at omega t plus phi equal to 0 and omega t plus phi equal to pi by 2. It is clear from this diagram that the negative charge goes from P1 to P2, tracing the circle in a clockwise manner, while the positive charge traces the circle in an anti-clockwise manner. But more importantly, the negative charge traces a right-handed circle. This is B, and it traces a right-handed circle, and the positive charge therefore traces a left-handed circle. So these are the two situations. Now if B is upwards, the negative charge will trace a right-handed circle, but the positive charge will trace a left-handed circle. So negative charge follows a right-handed circle. This is something we can remember. Let us solve a few problems now. This is the first problem. PQRS is a region of magnetic induction of value 0.05 Tesla. S is a source of alpha particles, and these alpha particles follow the path SQ, an arc SQ, and they enter into a reaction chamber kept at Q. Now mind it that SQ, as per the diagram, SQ forms 1/4 of the full circle. We have to find direction of B in this region and the time taken by alpha to move from S to Q along this path. Now to find the magnetic induction in this region is an easy task. if we remember that negative charge traces a right-handed circle with respect to the B field. Now here SQ is a right-handed circle with respect to B pointing up if charge involved is negative, but here the charge alpha is positive. Therefore B will not point up but will point down. We can verify this claim by a rigorous calculation. This is the Lorenz force. F is acting along SP, and V is along the tangent, that is SR, along SR. So the task is to find what is B. In other words, V cross what is F, and V is this, and F is along the thumb, so V cross B, so B must be downwards. So we have obtained the direction of B, it is into the paper, and the time taken to traverse is very easy. It is 1/4 the total time period, and total time period is known to be of this value. We just put the values in proper units, and then we end up with this time which is needed for alpha to move from S to Q. Now this is the next problem where two questions are being asked. One is, can magnetic field accelerate a charged particle? And the second one is, can magnetic field energize a charged particle? Let us come to the first one. This is the circle, some circle along which a charged particle is in motion in a magnetic field. Now at each and every instant the velocity direction changes, and direction of velocity changes means the particle is accelerating. So yes, the particle accelerates in a magnetic field. Again, since V, the magnitude of V is constant, therefore the kinetic energy is also constant. The particle cannot gain energy as it moves in a magnetic field. So the answer is therefore C, yes and no. We come to another problem where we are provided with a region where there is a magnetic induction, and this time magnetic induction is pointing up. Two circular trajectories have been shown, one corresponding to particle 1, the other one corresponding to particle 2. Now we have to interrelate the momenta of the two particles, the masses, the velocities, and then verify which option is correct. Now to solve this problem, let us bring radius into discussion, the value of which in terms of momentum is this one. Now it is given that the charges are same, also the field are same. So since Q and B are same, the ratio of the radii is the ratio of the momentum. So particle having larger momentum will be able to trace a circle of larger radius, and therefore since particle 1 traces a trajectory having larger radius, so the momentum of particle 1 will be larger. So m1 v1 is greater than m2 v2. In other words, option A is correct. Now in this problem there are three particles, one is proton, one is deuteron, one is alpha, and they are moving with equal kinetic energies. They enter perpendicularly into a magnetic field, and we have to find the radii of the circular path they trace. So this means that the radius again has to be brought into discussion, and since kinetic energies of them are same, we have to express radius in terms of their kinetic energy. So this is the expression which we got earlier. Now since kinetic energy is same, B is same, therefore the radii is proportional to under root m by q, m being mass of the particles and q being the charge of the particles. Now proton, mass and charge has been written. Deuteron, which is basically a PN system, its charge and mass have been written. Alpha is a 2p2n system, its charge and mass that also is there, and therefore rho p, rho d, rho alpha, the ratio is just this one, and if we put the values it turns out to be 1 is to root 2 is to 1. This problem has been repeated here, and instead of equality in kinetic energy, now it is said that the particles are passed through a region having same potential. So now the kinetic energy which they gain when passing through the potential is Q into V, Q being charge of each particle. So now the expression for radius in terms of kinetic energy will be replaced by QV, and therefore rho now is proportional to under root m by q, and therefore the ratio now takes a different value. Here we have again used this chart to put the values of the masses and charges correctly, and if we do that we end up with this ratio. We will now try to find the ratio of the time periods of those three particles, namely proton, deuteron and alpha. The expression of time period is 2 pi m by qb, and since b is same, therefore time period is proportional to m by q. Now m and q of each particle are known, so again as in previous problem we take the ratio. So Tp is to Td is to T alpha. This is the ratio of the time periods. This turns out to be 1:2:2 if we put the values correctly. In the next problem, we have a momentum filter having fixed source to detector separation. 5.3 MeV alpha move from source to detector along the circular track. Now the question is, what would be the energy of deuteron beam to trace the same path in a magnetic field of 2.3 B in order to be filtered out? So we have to compare the kinetic energy of deuteron and alpha in this problem. Now this is the expression of kinetic energy in terms of momentum, and we replace momentum by radius to get this expression, and here radius is constant. Since this separation is constant, so radius is constant, and therefore kinetic energy is proportional to q square b square by m. Now using this charge and mass values of alpha and deuteron is a pn system and alpha is a 2p2n system, p for proton, n for neutron. We can compare the kinetic energy. So if we put correctly the values of charge and mass of alpha and deuteron in this ratio, we end up with this value, and then let us put the value of kinetic energy of alpha, which is given to be 5.3 MeV. We end up with this expression of the kinetic energy of deuteron, and this is what was wanted in the problem. Next problem involves two particles, one having mass double that of the other, and they have equal charge and equal kinetic energy, and they are in the same field. We have to find the ratio of radii of circles which they traverse in the uniform magnetic field which they enter normally. Now this is the expression of radius, and we can express it in terms of kinetic energy, and since kinetic energy, charge and magnetic induction are same, the radius is proportional to square root of mass, and therefore the ratio of the radii is equal to 1:2. This is a similar problem involving four particles, electron, proton, helium plus and lithium plus, and they enter with the same velocity perpendicularly in a magnetic field. We have to find which particle traces the smallest circle. Now this is the expression of the radius, and since velocity is constant, magnetic field is constant, so rho is proportional to m by q, and we can therefore compare their radii, which turns out to be simply mass to charge ratio. And using this chart where we have listed the charge values of these four particles and mass values of these four particles, we end up with this ratio, and obviously the least value is possessed by electron. So electron will trace a circle which has least radius. So answer is A. In this problem, we have taken He plus to be 2p2n system and lithium plus to be a 3p4n system. 3 being the atomic number, 7 being the mass number. Let me end this lecture with the words of Buckminster Fuller, an American architect. You never change things by fighting the existing reality. To change something, build new model that makes the existing model obsolete. Yes, and only then the old will give way to the new. Thank you.